Hi, everyone. Yes, I'm Sam Williams. I'm from the University of Kent, and I spent the last 4 years building 2 operating systems with Erlang. And so I'd like to talk to you today about how you can construct these kind of software projects. But rather than just using my own experience, I thought it would be interesting to reach out to some of the other people that have built Erlang-like or Erlang-related operating systems as well. So yeah, I've integrated some of the experiences that the Erlang on Zen, Erlang on Rump Run people have also had. And what I really want to do with this talk is essentially put most of the design space information that you might need in order to build an Erlang operating system in one place. So it can give people a kind of head start. Because there's a lot of duplication, unfortunately, of mistakes that we've made in the past. So hopefully we can, yeah, make a solid foundation. Right. And critically, what I want to do here is discuss the design space. So to map out what are the problems that you're going to have to encounter if you build a system like this, and what are the potential solutions to those problems, and architectures and this sort of stuff. Okay, so first we're going to look at why you might want to build an operating system in Erlang to begin with, and then the existing systems that we have. We'll go through in turn their architectures, their strengths and so on. And then we'll look at uncharted territories, so potential ideas for future projects. We'll map out a couple of those, as well as looking at the challenges that are associated with it. So the questions you're really going to have to answer if you want to build a system like this. Then the lessons that we've learned as a community thus far with these kind of projects. And then we'll look a bit at HydrOS, which is the second operating system I built, and we'll use that as a kind of lens through which to look at these problems. And then a quick demo and acknowledgements. Right, so why would you want to build an operating system in Erlang in the first place? And there's a number of reasons, but the primary one for me, I think, is fault tolerance. Because obviously, when you're building an operating system, normally you use C or assembly, and recovering from failure at that level is not easy at all. So the fault tolerance primitives of Erlang offer a nice way of getting error recovery into your kernel and operating system. And there's also the scalability aspect. So as we look to a future with hopefully hundreds or thousands of cores on chips, the current operating system design, the sort of monolithic single kernel system that uses finer and finer grained locks over time in order to stop multiple cores in the system using the same functionality at once. It doesn't scale very well. So there's an interesting study done by the people that wrote an operating system called HydrOS. And they basically found that as you scaled up to 16 or 32 cores when you're running a web server, say, then you end up spending like a very significant amount of time doing lock contention. So that's not good. So yeah, I think with Erlang we can find ways around that, and we have, and I'll speak about that later. Another interesting thing that you get with an Erlang operating system is that you get a very high-level execution environment with interchange, or a nice interchange, or data interchange format between programs. So rather than just using text like you do with Unix, if all of your programs are written in Erlang, you can just pass functions around and pass deep lists and structures and things, which is really nice. And particularly the way that you can pass functions between programs is really quite cool at the operating system level. So the other thing you get is machine-independent programming environment, if you're using a VM, that is. And we'll get to that a bit later. So this is really nice if you're building, say, a distributed operating system. And what you could essentially do there is, because all of your operating system code is written in Erlang, it runs on top of the beam, and if you port the beam to ARM or x86, then you can run the same operating system code across those different platforms. So if you build a distributed operating system, you can now integrate the same, or you can run the same programs across your cluster, even if it's ARM, x86, or MIPS, or whatever you like. So that's quite nice. Yes, so first we'll look at Uni Kernel Erlang systems. Now, I'm going to use the word Uni Kernel quite a lot in this talk, so we better get clear what it means, just in case Yes. So a Uni kernel is essentially a program that is compiled into an operating system image that can be run natively on a machine or in a hypervisor of some kind. So the idea here is essentially you take the program and instead of deploying it on top of a traditional general purpose operating system in Amazon EC2, say, you instead turn it into a very small, very specified operating system that only contains the code that you need to execute your program, and then you run it normally in the cloud. And this has a number of advantages, primary of which is that, well, the images are smaller and there's zero configuration. You just run them and they work in cloud environments, which is rather nice. You don't have to move around very large images or anything like this. And also from a security perspective, it's great because you essentially remove all of the code that's not going to be used, so there's less for an attacker to use against you. So, for example, there's no console in Uni kernel systems. So if you get access to the machine, well, you'll have a difficult time attacking it. So that's the idea, at least. And there's also the fact that they can boot up extremely quickly. And this means that you could essentially, or potentially, boot up a Uni kernel in a cloud environment in order to respond to a single network request. So the architecture here would be that you have, say, one Uni kernel running, it receives the network requests, and then it can spawn another one that just goes and answers that, and that's all of your, that's all of your environment, essentially. And it's very small, very neat. And you only get charged for what you use, obviously, because if your VM is only alive for, half a second, well, that's cheaper than an hour on EC2. Yes, so the interesting thing about Erlang on Zen is that they built their own VM called Ling. And I've spoken to Maxim Karachenko about this, and he was talking about how one of their primary goals when they were writing this VM was essentially to lower the amount of time that it takes to get from starting the computer to executing the first Erlang instructions. And he said that he even counted the instructions from when the machine booted until those first beam instructions are or Ling instructions are executed. So I don't think you can really get. Okay, sorry, one of the screens changed there. I don't think you can really get faster time to Erlang execution than this. Right, so next we have Erlang on rump run. So rump run is a kernel it's a Uni kernel system. It's very small. It generates about 6 megabyte images with Beam on top of it. Yes, so the difference between Erlang on rump run, Erlang on Zen, is that Erlang on rump run uses the Beam, Erlang on Zen uses Ling. And the next is Erlang on OSV. So OSV is a Uni kernel system that creates fat Uni kernels. So Uni kernels that are much larger, about 80 megabytes in size. And the idea here is that essentially you have a much more Unix or POSIX compatible interface. And so that makes it much easier to port programs to the operating system and also to configure it. So yes, this was Erlang on OSV used in Erlang. So that's Erlang on top of JVM on top of OSV on top of hypervisor, typically. Yes, and that's quite interesting. And there's also EUC17, which is just Beam on top of Zen, which was my first Erlang operating system, which, yeah, best not go there. Right, so there's also Erlang embedded platforms. And these aren't quite the same thing, but they're certainly related. And so the first of these is GRISP, which is Erlang on top of RTEMS, which is a very small operating system, or I've heard it described as closer to a control program than an operating system. Right, well, precisely, yes. And yes, built so that you can create IoT wireless devices with Erlang, among other things, and targets ARM. It's also the Nerves project, which takes a slightly different approach, which is to run Erlang or Elixir code on top of the Beam, on top of Linux. But it's basically like the minimal amount that you require of Linux in order to run the Beam. So it's just the kernel and that's pretty much it, and the standard libraries. And one of the interesting things they're doing there is they're working to expose kernel functionality inside the Beam environment. And that's quite interesting because a lot of these other projects have worked to move operating system functionality out of the kernel and into the Erlang space. This is taking the inverse approach. It's moving parts of an existing kernel into the Beam itself. And there's also the Erlang Embedded initiative, where they created a small Erlang package that you could use on devices like a Raspberry Pi, and also an actor library from Embedded, which provides a nice way of interacting with like I2C devices, say, in an embedded environment. Right. So the final operating system is HydrOS, which is, as far as I'm aware, the only general purpose operating system, so written in Erlang. And it's for servers and desktops, x86 machines generally, really. And it focuses on providing fault tolerance and error recovery from typically catastrophic OS failure. So things like, or things that would normally cause a blue screen of death, for us, just lose a core, and then we restart it, and it works. And we'll talk a bit more about that later. And I'll also have a demo where we'll do exactly that. Yes, so it's written entirely in Erlang from the ground up, or at least as much as we could put in Erlang. So there's really very little by way of kernel. It's just Beam on top of, bare metal. Right, so here's two ideas that might be interesting for people that are looking at building an Erlang operating system. One of them is truly native Erlang code running as the kernel of the system. So the idea here would be that you take hype, or potentially the new JIT, and modify it such that you can create a kernel written directly in Erlang. And there's an interesting idea here with how you could use this in a cloud environment, where you could essentially create Uni Kernels with this system that could launch other Uni Kernels as processes. So you essentially have Uni Kernel processes with the hypervisor providing a scheduler to the system. And this is quite interesting for a number of reasons, one of which is the potential for, so I was saying before about how Uni Kernels are specialized. Well, if we had Uni Kernel processes in Erlang, if we specialize them, we'd remove all of the modules that you don't need in order to execute that process. And if you do that, you can start to create a sort of disparate space where if an attacker tried to get into your system, they couldn't access all your code. It wouldn't be in the same environment. So even if there were parts of your system that could be used together for some malicious end, say with return-oriented programming or something like this, they would have a hard time doing that because they'd have to break out of the VM instances of the hypervisor, which certainly happens sometimes, but it's a pretty significant task. Another thing that you could look at is creating a small Erlang VM for many core devices. And one of the things I'm really interested about with this is the potential for hardware message passing. So it seems the Erlang model would map very well to hardware message passing, but the platforms haven't really caught up with where we'd like them to be so far. But there are starting to be some platforms that allow you to do this. So having an Erlang operating system that actually used hardware message passing would be pretty interesting. Right, so now we'll look at the challenges associated with Erlang OS design. And the primary one of these is, obviously, if you're going to write an operating system in Erlang, you're going to have some way of executing Erlang code. So, and this is the primary architectural decision you're going to make, because it changes the entire way that the system runs and the performance and fault tolerance characteristics of the system. So it's very important to get right. So will it be native, or will it be interpreted, or will it be interpreted within another VM or OS, like, say, the nerves system would fit into that category? And also, at what level will it be Beam compatible? So are you going to run Beam instructions? Is it going to use like half the Erlang compiler and then have a new code generator at the end? Perhaps you'd do that if you wanted native native code execution? Or are you going to use a Beam code transpiler? So this is essentially what Ling does, where you compile stuff into Beam, and then you take the Beam instructions, you compile them, or transpile them into Ling instructions. So these are pretty fundamental choices you have to make. So now we'll go through some of the potential architectures that you could use to write an Erlang operating system. The first being Erlang on Metal. This is, you get your Erlang code, you compile it to native code, you run it on the hardware. It's pretty simple. And probably the most efficient, too, if we could actually get it to work. So the second is the virtual machine operating system. This is essentially where you have your Erlang code running on top of a VM, possibly Beam, probably Beam. Yes, and that's how you organize the system. Or you could have a multi-kernel system whereby you essentially have one VM per core in your machine, and then you have a distribution layer on top that unifies the virtual machines, and this is what we've done with HydrOS. Another potential way you could organize the system is to have Erlang code running on top of a VM, running on top of the hypervisor, running on top of the hardware. So this is what happens, say, when you run Erlang on Xen. This is the kind of stack you have. Or you could get a distributed Uni Kernel Erlang. And this is essentially similar, but you have a distribution layer across your Uni kernels on top. And this is rather interesting because if you add code such that your Uni kernels can spawn other Uni kernels, then you can expand the system in the cloud as you wish, or yes, and contract it too. And the final architecture that we'll talk about later in this talk, if we've got time. Oh, good. Unfortunately, clock has stopped running. Thanks, Android. Right. Wonderful. Okay, so essentially in the multi-uni kernel system, what we do is we take the multi-kernel approach, which is split every core into, or split the machine into a set of independent cores, allocate some memory for each of those cores, allocate a kernel copy for each of those cores, and then they all execute independently, but they interact and communicate at the Erlang level and coordinate program execution. But we take that idea, and instead of having the same kernels across all the cores, we can replace some of the multi-kernel nodes with uni-kernel nodes. And so here we essentially run our C code alongside our Erlang nodes and run our app across the top of them. But I'll get into that a bit more later. So another critical decision you have to make is where you're going to draw the lines between what's implemented in C or assembly and what's implemented in Erlang. And this is really important because it has a number of fundamental impacts on the way your systems will behave in practice. So will your drivers be written in Erlang? How about performance critical GUI code? You know, if you do this, you're going to take a pretty significant performance hit, unless perhaps you're using the native code system that I was, or a potential native code system that I was talking about earlier. Yeah, and so in HydrOS what we do, oh, that's cutting off the bottom of the screen. Okay. In HydrOS what we do is we have the local kernel, which is written in C, which is essentially just a beam with the absolute bare minimum by way of library functions that is required to make it run. And what we do is we try and minimize the amount of functionality that's written at this level so that we can recover from failures better, because obviously when we experience failures in C and assembly, much harder to recover from them when they're in Erlang. So we've taken the fault tolerance approach, which has some pretty significant effects on performance. But the critical thing here is that we keep the C code out of all of the distribution layer. So the C code runs in an environment where it doesn't touch any other kernels ever. And yes, this is quite nice because obviously it limits the potential for failure cascade, which is pretty bad in these kind of systems. And so yes, and then we have our Erlang code on top that runs all of our drivers and interprocessor communication and all of this sort of stuff. Right, so most Erlang systems will use at least some C or another language, or they'll have to interact with another language at some point. So you have to ask the question, well, okay, if you've got an Erlang operating system whereby you've got the beam, say, running directly on the hardware, how are you going to execute that code? And indeed, how are you going to load it? Because one of the nice things you can do if you've just got the beam running on the hardware is you just map the address space linearly, and you can compile the system so that it knows it'll be loaded. In HydrOS, it's loaded at 1 megabyte, and it's loaded there every single time. So there's no loading done at runtime. Everything is pre-computed. But if you're going to incorporate C crypto libraries, say, you're going to have to find a way of doing that where it'll load and execute properly. And yes, so there's a problem with drivers. If you use C drivers, so a nice way to organize a system you'd think might be to have most stuff in Erlang, but then your drivers, which are high performance, are written in C. But then you have the problem of scheduling. So with HydrOS, we just run beam on the core, and it's never interrupted. It just does its thing. But if you've got drivers, you've got to work out how you're going to execute some, or you're going to allocate some CPU time to running those drivers. So one of the ways you could look at solving this problem, if you did want to have native code drivers, is you could try and write them in an event-driven way. So they only execute code in response to interrupts. And this way, once you get the interrupt, you registered with the interrupt handler already that you want this piece of code to be run when you receive this interrupt. It does its thing. You deassert the interrupt. You return to the code. And that's how you do scheduling. But there's potential problems of starvation there. So if you receive a lot of interrupts, and potentially a lot of interrupts in a row, you might just never execute VM code. And it's also, there is a number of devices that I don't think this kind of system would work for at all. You would have to have some kind of process attached to them. But it's something to think about. OK, so actually getting your operating system to the point where it can execute Erlang code is non-trivial. I mean, when you start an x86 machine, you have one core in 16-bit mode. Getting from there to having all your kernels loaded and in memory and all of your cores running and in 64-bit mode is really quite a journey. So I would suggest that if you can, you use a bootloader, a pre-made one like Grub or Lilo or syslinux or something along these lines, which will certainly help you out. But unfortunately, for a lot of the architectures that I mentioned in the previous slides, there are differences that really make it so that these bootloaders don't offer you very much. And for HydrOS, we essentially ended up writing our own bootloader, because you need a kernel for a copy for each core, and then you need the page tables loaded such that each core thinks it's using, each core thinks it's at the start of memory. And there's a number of complexities that essentially meant that actually doesn't really offer you that much. One of which is that when you start additional processes, additional cores in the system, they start in 16-bit mode. So if you're going to execute your code in 64-bit mode, you're going to have the mode switching stuff that'll get you there anyway, which is kind of half of the job of what the bootloader's doing. So yeah, there's some intricacies there. And there's also the idea of securing an Erlang operating system. So one of the things that the Beam is like an operating system in many, many ways. It does device abstraction, memory management, processes management, scheduling, all of this stuff. But one of the things it doesn't do very well is security, because it sort of assumes that that's going to be done by the operating system at some other level, and the edges will be protected. So if you want to make an operating system in Erlang, and you want it to be secure, you're going to have to come up with some sort of system for that on your own. And if you just decide, say, that you want to protect the edges of the system, then are you okay with the fact that applications inside the system can just interact with each other arbitrarily? So I could run an application and it could get a list of all the PIDs in the system, and then I could send kill to all of those PIDs, and there's a likelihood that maybe one of them, or exit rather, there's a likelihood that one of them will be like, oh, okay, sure, you want me to exit then, that's fine. So there's no application isolation in Erlang as it stands at the moment. So if you want to, if you want to have a secure system, then you're going to have to come up with some solution to that problem. So 2 fundamental lessons that I think we've learned from Erlang operating system development in general. The first is that your operating system is going to have to be placed on the fault tolerance performance spectrum somewhere. There is no way you can really get around this. And so obviously native code is fast, but failures are harder to recover from. And Erlang code is slightly slower, but you have really nice fault tolerance characteristics. And another interesting thing that came up when I was speaking to Maxim was the potential for not needing SMP support. So having VMs that are single-threaded, talking to each other at the Erlang level and doing distribution that way. And he says, this simplifies the implementation greatly and speeds things up. The philosophy is that you need more VMs to achieve true multi-core parallelism. Hypervisor is the only hardware scheduler. Erlang processes are green threads. And this is a similar approach to what we've done with HydrOS, where each of the multi-kernel cores runs its own VM. And this is also quite important if you're writing a Uni Kernel operating system that doesn't normally use multiple threads. So something I got by speaking to the creator of the Erlang on Run system was that if you can get away without fork, that would be really good. And so with Erlang, you can configure it such that you can right now, but somewhat changes in R20. You can use the plain system, which won't fork, allows you to run a single thread Erlang system. Yeah. So now we're going to look at HydrOS. So HydrOS uses a multi-kernel architecture, where you essentially take the cores in the system and you split them, you take a single machine, you split it into a set of independent cores, and you allocate memory to each one of those cores, and then a kernel copy to each one of those cores. In our case, the kernel copy is really just the beam with tiny bits of library code added to it to make it execute on bare metal. And then we have a distribution layer written on top of that, essentially. And you can see in this example that we've got a Uni Kernel, which is a multi-Uni Kernel system that we'll talk about in a second. So one of our fundamental design decisions is that essentially we needed failure on one of the cores not to affect failure on, or not to affect execution on other cores. So because the VMs are isolated, we don't mind if there's a massive software failure, say like a blue screen of death level software failure, or potentially even a hardware failure in the core. As long as there are other cores available in the system, and this really means as long as the failures don't happen on all the cores at once, then we can restart the core if it's still functional, or we can just ignore it. And obviously, you can use your Erlang fault tolerance primitives to monitor and get messages when when processes that were hosted on a VM that has failed are no longer available. So you can recover from it quite nicely. OS subsystems and drivers are also isolated from one another in the sense that they're split into many smaller processes. So failure in one of those processes obviously doesn't affect the other processes, and we can recover from it, hopefully. And there's also potential for decentralization of this system in the future. So we're really interested in making systems that are tolerant to almost all kinds of faults, and obviously having a centralized structure makes that much harder. But if each of the cores in the system could act independently, it'd be quite interesting. So HydrOS uses a system of Biss, which interact directly with the hardware. And essentially what we did here was try and keep them as small as possible, because obviously if you get a failure in the Biff, we can actually recover from some of these kinds of failures. And we use a system whereby essentially if you get a general protection fault or something of this ilk that we can't normally recover from while running the beam, say, we just kill the process that was running at the time the interrupt happened. And then we re-enter the beam main interpreter loop rather than returning to the previous place we were in execution. And sometimes this works, sometimes it doesn't. But yes, certainly there's some failure recovery there. But critically, we wanted to keep the Biss as short as possible so the likelihood of failure inside them was very low. And these are really just things like enabling and disabling interrupts, everything above that level. In fact, a lot of them are just wrappers for instructions. Everything above that level is implemented in Erlang. Yes, so HydrOS uses Erlang-only drivers, which, as I was saying, are sets of communicating processes that are distributed across potentially multiple nodes in the system. And we use this thing called the I/O APIC, which is the Input-Output Advanced Programmable Interrupt Controller, which can only be named by engineers, I think, to route interrupts around the system. And this is kind of interesting because it's essentially the router of the network. Yes, we can make it so that the interrupts go to a specific core where the main driver is found for that device that it's attached to, or we could duplicate all of the interrupts and send them to all of the cores, which is quite nice. And we've got Erlang control over this, so you can just call a function in Erlang and it'll start routing interrupts in a different way. So one problem that we have with this, well, it hasn't yet become a problem, but we think it will in the future. One problem is that for level-triggered interrupts, so essentially what Erlang, in fact, on the next screen I can show you. So the node kernel, this is the C part of the system, when it receives an interrupt, the interrupt handler runs, and it essentially just sends a message saying, okay, I've got this interrupt number to the interrupt dispatcher, which is an Erlang process, which then has the routing table of who wanted to hear about which kind of interrupt. And here in this example, we've used the keyboard handler. So, okay, interrupt 33 means a key was pressed. So we send the interrupt round to the keyboard handler. Keyboard handler reads the data from the device, passes it, does, turns scan codes into characters, this sort of thing, sends keyboard events to people that have registered to listen. But critically, what's going on here is the node kernel will send that message, and then it'll deassert the interrupt and return to execution. And this means that that message won't have actually got to the Erlang program, and it won't be, or the reason for the interrupt won't have been fixed by the time the interrupt is deasserted. And there are some kinds of devices that if you do this sort of thing, they'll just instantly reassert the interrupt, which means that you end up back in the interrupt handler, so you just send endless messages until the program or system crashes. So that's a potential problem we're going to have to fix. So HydrOS window management. One of the new things I've built with HydrOS since last EUC. How am I doing for time? 5? 10. Oh, great, thanks. Yes, we built a window management system. So essentially you have a set of full-screen console applications. We wanted to be able to multiplex between them. But this led down a rather interesting road where we ended up creating sort of composable window interfaces. So we have a window process, which essentially just has a buffer, and you can write to it. It says, okay, at what location would you like to write? And you say, write this string and do it in red, and the background will be green, or something like that. But on top of that, we built a system of more abstract, essentially, interfaces, like a terminal. So you can start a terminal process, which will then start a window process. And the terminal keeps track of where the cursor is, the scroll position, all of this sort of stuff. And it sends render requests in the form of print this at this location to the window. And what you can do is you can then just send your messages to the terminal rather than the window. And it'll handle all of that complexity for you. And it's generic. And you can build them on top of each other repeatedly, which is interesting. And we'd like to go into this a bit more with potentially building a forms system. So you might have a form running on top of a window, and then you might have button processes or what have you running on top of the form. And so you get composed interfaces like that. Yes, and another interesting thing about the window management system is that it requires the window managed apps have at least two processes. So you have a process to which all of your keyboard input and mouse input is sent, and then you have a process, or a window process. And this leads to systems that are designed a little like this. So you have the keyboard driver sending key events to the input process, and then the input process sends render commands to the window, and the window, if it's in the foreground, writes to the text buffer. So here with the HydrOS console app, essentially what we have going on is the keyboard input comes into the input server, and it builds up a string until you press enter. Then it sends that string to the worker process that tries to execute it, waits for a response, sends the response back to the input server, which then prints the string, just tells the terminal to print the string, and the terminal says, oh, okay, well, the cursor's here, so we want the string to be printed here, and it does scrolling and this sort of stuff. And then, the render commands go out to the window. Okay, so finally, HydrOS multi-Uni kernels. So it's a bit of a mouthful, so we call them MUCs. They're essentially cores in the system that are running C code directly in real time, rather than a normal HydrOS multi-kernel node, so not running Erlang. And one of the interesting things you get about this is that you get, I don't think you could configure a system such that you get more performance out of it. Your code will run uninterrupted on a core, and you can do whatever you like with it, which is quite interesting because say you have a 100-core system and one NIC, then it might actually be efficient to write what we call a Uni Kernel driver, which is essentially just a single core in the system that you dedicate to servicing the piece of hardware at the maximal possible speed or throughput. Yes, and there's the typical library for interacting with Erlang nodes on top of this. And one of the things we changed since last EUC was it's now really, really easy to build these things. As long as you can get HydrOS to build, which there's instructions for on the website, you just go into a directory, you add a subdirectory, and put a C file in it. And as long as it's got a kmain function, it'll just compile and link and run properly. So I made an example hash farm system that you could send it a request, and it would hash that request a number of times. And I managed to get it down to like 50 lines of C with no associated make file or anything like that. You just put in a file, it runs, which is quite nice. But if you want to build more complex systems, you can put in your own make file. It'll not use the default one, and you can make it as however complicated you like. So here's an example multi-Uni kernel or potential multi-Uni kernel system that's, say, running a web service. So you would have a network attached processor, which is just talking directly to the NIC, and then potentially a cache in front of that, because obviously this is C, you can do it exceptionally quickly. And you could then potentially send requests to, so I don't know, maybe it's a service that does adding filters to images, something like this. So if you had a filter image request, you could then send it to a GPU-connected Uni kernel, which just manages the GPU directly. And you could send the HTTP requests to the Erlang program, where that's sort of a more suitable way of handling it. And so the critical idea here is that you use the right tool for the job. So if it needs to be fast, go with Erlang. If it needs to be, if it's fast, go with native, if it's slower, or it doesn't need to be so fast, go with Erlang. And you can compose these systems to make essentially microservice real-time Uni kernels. So here we have a potential, sort of Facebook-esque system where you've got user account management as well as a social graph search function and file storage. And these 4 cores at the top here are all running potentially different programming language environments even. So, thank you. So you could port a Prolog VM to run on top of a HydrOS Uni kernel, and then you can just embed your Prolog program into your HydrOS deployment. And again, right tool for the job is the thing we're trying to stress here. Oh, and just one other thing. A nice thing about this is that you get HydrOS to orchestrate the system for you. So if kernels crash or something like this, it can restart them, and it can potentially even swap them out at runtime, all this sort of stuff. And another point just to make very clear is normally Uni kernels run on top of a hypervisor. But in this system, the Uni kernel runs directly on top of the hardware. There's nothing between you and the hardware, which is interesting. So security in HydrOS. I'm going to skip this, actually. But basically, very quickly, we create trees of decreasingly capable processes. So the idea is that the root process in the system can do all things, but then when you spawn another process, you can say, okay, this process shouldn't be able to do this kind of thing, say memory access. Or, and it's a rich language, so you can say memory access between this range and this range, say, or ports here and here. And then all of these, the children processes of that new process won't be able to do those things either. So you make a tree where they get less capable at the bottom. And a nice thing you can do with this is you start a console, but you say, okay, don't let it have raw memory access, or don't let it have raw port access. And then somebody gives you a dodgy beam file. You know, I don't really trust this. So you run it inside this sandboxed console, and it tries to cleverly add memory access between some addresses that it'd like to use, but it can't do it. It'll just fail, which is quite nice. The other way you could look at it is if you're writing a driver, say, that does, I don't know, pointer arithmetic, say it's using a memory-mapped device. There's potential that your driver will go wrong, it'll access memory outside of where it's supposed to access, could break the whole system. So when you write the driver, you can just specify, okay, when you spawn it, just spawn it with these capabilities. I only want to use these 2 ports. So if I try and do anything else, you know, don't let me. And that's kind of nice. Okay, so very quickly. So here is HydrOS booting in QEMU here. Right, so here's the terminal, and now we're going to show the shortcuts that are available from the terminal. So here we're going to start the shortcut associated with F3, which is essentially a ping-pong program, which takes, it spawns 2 processes, one on each core in the system, and then starts pinging-ponging between them. Pretty simple. So we can see it's pinging, and now we go to the system log, and you can see here that we're receiving and sending messages. And then here we're switching the window to another console. And on this console, we're going to show the shortcuts again. And this time we're going to run F7, which spawns a process on the other core in the system and runs an unsafe interrupt, by which we really mean dereferencing an exceptionally large pointer in the beam. So this is pretty error-ridden stuff. Normally there's no coming back from this. So we run it, and you can see here, normally the horrible gray tile wouldn't appear, but I've left it there so you can actually see something's happening, because otherwise there would be no output. So we can see that it's detected that failure, it's restarted itself. Now we're going to go back to the previous console, and you can see that the process that was found on the first core of the system is still running, it's still waiting for the process on the other core in the system, but it's failed. And you could very trivially change the program so that it would detect this failure, restart it. Obviously, it's detecting the failure because it's printing that it's waiting. So now we run the ping-pong program again, and you can see that it's pinging backwards and forwards. So we've reestablished connection, we've reestablished execution across both of them. And that's killing an entire core in the system. It really doesn't get much worse than that. And we've maintained functionality. So yes, acknowledgements. I'd like to say thanks to Simon, my supervisor at Kent, and also Maxim Karachenko and Niraj Sharma from Erlang on Zen and Erlang on Run for their contributions. I really appreciated talking to them, as well as the HydrOS contributors. So our 2 students, George Bates, who worked on the original implementation of the keyboard handler, which ended up being quite interesting, and George Forward, who wrote a file system for us, which I didn't get time to go into today, but we can now write to files, so that's nice. And also Anton Tomasson, who very kindly implemented keyboard mapping for Swedish keyboards. He's also now working on EFI support, which is great. And part of that is also looking at using a proper graphical, a proper graphical terminal to start with, but then later potentially more graphical things, so proper GUI interfaces. And EPSRC for funding me. Okay, so you can find it at hydros-project.org. I released the latest version last night, so it's up to date there with the development branch. And I can be contacted at this address. And I'm always interested to hear from people that are interested in this kind of stuff. So thanks.
Thank you very much. We do have time for a question or two. So, Pierre.
So first a remark, Grisp does not target ARM, but it targets ARM and PowerPC and Spark and MIPS and everything that has 32 bits at least.
Right.
It runs on everything. And then a question, I have difficulties getting the reason for, I mean, I think I get the reason for running separate VMs on separate cores, but isn't the actual reason because most of the existing Uni Kernel systems don't support SMP? Because it looks wasteful to me.
Not for us. We really care about fault tolerance, and we didn't want to have errors potentially happening at the C level with SMP beam. So, yeah. But certainly, for a lot of Uni Kernel systems, having single-threaded things works better. Yeah.
By the way, Grisp has SMP.
Right. Yeah. No, but not all. Certainly. Yeah. Absolutely. But no, for us, we were really motivated by fault tolerance. That's why we went down this path to begin with. So having the VM split. Okay, yeah. Well, because the errors don't happen in the distribution inside the beam. You don't have C schedulers. So if you lose one of the schedulers in the system, well, we do that at the Erlang level. We lose a VM instead, and so we can recover from it in Erlang. Whereas if you lost a scheduler, which is written in C in the beam, you might have a harder time.
Any more question? I have a short one there on the security that you showed, although it was very quickly. So you limit the capabilities of each process. Is there any tool set you use or kind of way of reasoning about whether you limit it too much or too little for the safety purpose that you have at hand?
Not currently. It's really down to how the user wants to use it. I mean, yes, if you mess up, then you mess up. That's certainly, yeah.
And I can point you to some type system-like things that Lars Pareto did before.
Yes.
Where you kind of have the type system for capabilities and resources.
Yeah. There's certainly a lot that you could do with static analysis of the capabilities. But we're building an operating system, so there's a very, very wide space of things to do and not so much time to do it in. So we have to pick and choose.
I appreciate it. Okay, thank you very much once more.
Thanks.